Okay, it looks like we've settled into a steady state of people joining now, so I think it's a good time to get started. So we're very happy to welcome Radu Coldea, visiting us all the way from Oxford University for our first colloquium of 2021. Radu is a Walter Stern Fellow and Professor at Lincoln College at Oxford University. He received his PhD from Oxford, working with Roger Cowley. And then after that, he went on to positions at Rutherford Appleton, Oak Ridge, and Clarendon Labs, before holding an EPSRC fellowship and lectureship positions at the University of Bristol, and then moving on to his position at Oxford. So Radu is really a renowned expert in inelastic neutron scattering and magnetism. I think, for one, many researchers working in this field owe him a great debt for his authorship of a computer program called MSlice, which for some time was the only way that people doing these inelastic neutron scattering experiments could look at their data in kind of a reasonable, practical manner. Before that, there was just a lot of data sitting around, not doing much. So Radu is really known for being, I think, very creative and rigorous in his research in general. And for anyone hoping to learn about inelastic neutron scattering or frustrated magnetism, it would probably be very hard to do any better than just going through and reading all of his papers. So we're very excited to have Radu presenting at Colloquium today. So welcome, Radu. Looking forward to your talk.
All right, thank you very much, Kim, for the very kind introduction, and I'm very grateful for giving the opportunity to present to you and your colleagues some of our research in quantum magnetism. So in my talk today, I'll discuss our experimental exploration of topological magnons in a honeycomb quantum magnet. This research is complementary to other studies of electronic properties of graphene and semi-metallic systems, where the symmetry of the crystal lattice and interactions guarantees that there are touching points between the various bands. And here I'm going to explore this phenomenon of band touching effects in the context of an insulating ferromagnet, where the propagating quasiparticles are not electrons, but are actually particles carrying spin, they're bosons, but they also show the phenomenon of linear band touchings, as exemplified in this figure here. And in particular, I'm going to focus on the intensity distribution around these nodal points. And this has also a very non-trivial characteristic pattern associated with the topological properties of the touching point. So let me start by acknowledging my collaborators. This work is part of the PhD project of Miska Elliott, who was a graduate student in our group in Oxford. For the experiments and the analysis, we collaborated very strongly with Paul McClarty from Max Planck Institute in Dresden. He did all the theoretical calculations relevant for the analysis of the experimental data, and he deserves a lot of the credit for the depth of understanding that we've been able to reach. The crystals were grown by Dirac in Oxford using an image furnace indicated in this image here. And Roger Johnson focused on analyzing powder neutron diffraction measurements to understand details of the magnetic structure. And these were important to relate back to the spin and orbital magnetic ground state of the ions relevant for this material. The experiments were done using the ICIS pod neutron source in the UK, powder measurements by Pascal Manuel using the WISH instrument, and the inelastic measurements we did on the instrument Merlin in collaboration with Helen Walker. And this research is sponsored by a grant from the European Research Council. So in my talk, I'm first going to give a brief introduction to the phenomenon of linear band crossing, which is familiar probably to many of you from the context of single layer graphene. And then I'm going to discuss an analogy with the physics of the honeycomb ferromagnet, where now the hopping quasiparticles are spin flips instead of electrons, but a very similar type of band structure occurs. And then I'm going to show results of inelastic neutron scattering experiments, where we probe in detail the magnon dispersions, and then we focus on the nodal points, and also on the anomalous intensity modulations around these nodal points. And this particular material, based on cobalt, has the advantage that also not only spin excitations, but also higher order spin-orbital excitations are available. And I'm going to explore the dispersions there too, and find similar band touching points and similar topological properties there as well, indicating some universality that occurs for different types of bosonic excitations hopping on the same honeycomb lattice. And then finally, I'm going to describe some unexpected features we've seen in the experiment. In particular, the spins are ordered in the XY plane, but semi-classically, there's no mechanism to explain why they have a gap. And then we do see a preferential ordering direction and a gap associated with this. And then I'm going to describe possible mechanisms based on going beyond the semi-classical description to understand the origin of the spectral gap. So if we start with a familiar example of a honeycomb lattice of carbon atoms, this is graphene, where each blue ball is a carbon atom, has 4 electrons, 3 of them are locked up in bonds, but there's one in an orbital that's orthogonal to this plane, which can hop onto neighboring sites with a transfer integral T. And if we consider a time-binding model to explain the dispersion relations of an electron that hops between these A and B sublattices, we find a relatively simple result. It's a modulus of this function gamma k, which is basically a sum of exponential terms associated with hoppings across the 3 links. Now, there are 2 dispersion surfaces that are mirrored with respect to 0 energy, and they touch at the corners of the hexagonal Brillouin zone, these 6 points indicated here. And at these positions, the energy is 0 in both cases, and this coincides also with Fermi level of graphene at half filling. Now let's consider an important property here is that the degeneracy survives also if further neighbor hoppings are included, as it is a fundamental property of symmetry of the Hamiltonian on this lattice. So let's consider now a magnetic analog. So a ferromagnet on the honeycomb lattice, where now the exchange interaction, if it's ferromagnetic, okay, my video is back on now. Can everyone hear me?
Yes.
Yes.
Yeah, sorry for that. I had to reset my camera. So, okay, so now consider that we flip a spin on one side, and through the exchange terms, then this spin flip can hop onto the neighboring sites, again on the same links as before, with the only difference now that the hopping T is replaced by the exchange interaction J, and now we have a boson, an excitation with delta SZ -1 relative to the ground state, which hops. But formally, we obtain the same dispersion relation, only offset in energy. So again, there are two bands which we associate with the acoustic and optic magnon branch, and they touch the corners, the 6 corners of the Brillouin zone. Again, and the dispersion is linear, starting away from these points. So let's try and understand visually where this degeneracy comes about. And the magnon is a spin wave propagation where, if we consider here a representation with the equilibrium, all the spins were vertically up, then a spin wave means that we've taken a spin away from equilibrium, and then through exchange, this drags along all the neighboring spins, and then spins rotate both as a function of time and position with a phase, which is this projection transverse to the equilibrium direction. So if we refer this picture now to the dispersion relations for the honeycomb lattice, and we focus at the corner of the Brillouin zone, this particular touching point here, and if we take a section of the honeycomb, just consider one spin on the A sublattice. This is an orientation at a particular time, looking from above. So the equilibrium direction comes out of the page, and this is now the tilted spin in a spin wave. Now, the other sides on the A sublattice have a phase that's directly related to the magnitude of this wave vector. And then at this particular K point, the angle is 120 degrees. Now, the spins in the other sublattice, on the B sublattice, in projection, they can be either parallel or anti-parallel, meaning that we have an in-phase or out-of-phase magnon or acoustic or optic. And precisely at the corner of the Brillouin zone, where the angle between the A spins is 120 degrees, then the interaction with the spin up here for the perpendicular component cancels, because all of these are pointing at 120 degrees away from each other. So these two states are degenerate. This spin can be either parallel or anti-parallel, and in principle can be in any direction. The energy is exactly the same. However, this is not the case if we move a little bit away, because then the angle here is not going to be exactly 120 degrees, but a little bit different. And these three spins would create then a net field here, which will pick up different energies for the in phase and out of phase. And that gives rise to the splitting here, the immediate splitting, which is linear in the displacement of the K vector, because that this is associated with a linear displacement in the phase, and then a net field that gives rise to splitting. So fundamentally, if we go away from the K point in any direction, then there will be a net field, which is proportional in the first approximation with the magnitude of K, and then the energy will depend linearly on K. And this is the essence of the degeneracy and the linear dispersion in the case of the magnons. So at a particular point of the Brillouin zone, there's a cancellation of the interactions between the two sublattices that gives rise to the degeneracy, but moving away, that cancellation is gone, and then we've got a linear dispersion. So we're going to explore this physics in the context of a honeycomb ferromagnet, cobalt titanium oxide, where the building blocks are a honeycomb lattice of cobalt ions. These are the blue balls here. Each one is inside an oxygen 6 octahedron, and these octahedra are edge sharing. And they naturally form this edge sharing bonding geometry, giving rise to a honeycomb. And then successive layers are stacked up along the vertical direction. Say if we pick an origin of the honeycomb here, then the next layer would have the origin at this site here, the next one there, and so on. So the 3-layer periodicity up along the vertical direction. An important point of this is that the 3-dimensional stacking doesn't introduce a new number of sublattices, but can still be described in still in terms of a primitive cell of 2 sublattices. So for a single layer, we have sublattices A and B, but even if we go to the 3D stacking, this can still be described formally through a rhombohedral crystal structure, but fundamentally just with 2 sublattices A and B. So understanding the physics of sort of edge-shared honeycomb arrangements is actually quite interesting from other points of view as well. So here is a generic phase diagram for cobaltates in this type of bonding geometry, where the vertical axis characterizes how isotropic the environment is. So cubic octahedra would correspond to the 0 point here. And then the vertical axis is a trigonal distortion. And one direction is compression, and the other one is elongation along the direction normal to this plane. The horizontal axis is related to electron correlations, where here is the Hubbard interaction, and delta is some charge transfer energy between the oxygen and cobalt. Now, the material we're going to explore is in this orange corner of the phase diagram, corresponding to ferromagnetic alignment in each honeycomb layer with spins in the AB plane. Now, if we were to go to the red region here, this would also be ferromagnetic, but spins along the z-axis. And both of these phases would be expected to have topological magnons. Now, there are other ordered phases in this phase diagram. For example, ZZ stands for zigzag order, where spins form alternating zigzag chains oriented one way and alternating the other way. And here again, the ordering direction varies from being in the plane, out of plane, and this is some cobalt oxide direction. Now, very interestingly, also in this phase diagram, there's this deep blue region here, which is very close to the isotropic cubic octahedra limit, which is predicted to be a spin liquid phase stabilized by the frustration between strongly bond-dependent interactions. So say along the three directions that emerge out of each point, Ising interactions that favor orthogonal directions, say along some cubic directions, X, Y, and Z. So in general, exploring cobaltates with edge-sharing geometry could potentially be complementary to current research that may be familiar to some of you of looking for such type of Kitaev spin liquid physics, but in the context of 4D and 5D materials based on ruthenium and iridium. And of course, cobaltates, because they're easier to synthesize and so on, they offer completely new opportunities for exploring this type of physics. So I'm going to focus today on this material cobalt titanate, which is in this ferromagnetic part of the phase diagram, which spins in the AB plane. So this material has been known for some time to have a ferromagnetic order which spins in the plane, and also antiferromagnetic stacking along the vertical direction. And we've recently revisited that with powder neutron measurements and verified this model for the magnetic structure, and also obtained the magnitude of the ordered moment in the ground state. So here is a comparison between powder measurements at high temperature and at low temperature. There's a lot of new magnetic peaks associated with this type of magnetic ordering. And I might come back later in the talk to explain how this magnitude of the moment gives us insight into the spin and orbital mixture of the magnetic moments in the ground state. So here's a picture of our sample mount for inelastic neutron experiments. Here we need a large sample mass, so we use 2 co-aligned single crystals to be able to have enough scattering centers to obtain a good signal. So here's a picture of the elastic scattering. So this gives us the information about the ordering, and these red spots are associated with a particular type of antiferromagnetic order. The fact that one occurs every 3 zones is associated with the certain stacking that occurs between the layers. And if we sit at one of these positions and measure the intensity as a function of temperature, that naturally goes to 0 at the transition temperature through a nice order parameter. And this coincides also with an anomaly in the susceptibility at similar temperature to what's been seen in other studies as well. So that sort of confirms the stoichiometry of our sample and the high purity. So here's a picture of the inelastic neutron scattering measurements. So here is the spectrum as a function of energy vertically and momentum in plane horizontally. And the dominant response here is a very strong linearly dependent dispersive mode that's soft, close to the magnetic Bragg peak position. And this is characteristic of systems that have a strong easy plane anisotropy, where the spin fluctuates very easily in the plane. That's the dominant interaction, where there could also be a gapped excitation out to the plane. But we were not the first group to look at the excitations of this material with inelastic neutron scattering. Here's a reference to a recent publication where you can find complementary measurements as well. We focused somewhat on different aspects, which I will describe in more detail. So these are measurements for the dispersion for wave vector in the honeycomb layers. And then we can also probe the direction vertically up. And then we can see that, say, starting from a magnetic Bragg peak, there's also strong dispersion in the interlayer direction, indicating that the interactions are comparable, are important both in the layers and out of layers. Now, an important property that we see is that the spectrum has a very small gap, finite but small, above the magnetic Bragg peaks, as you can observe it here. So the way we analyze this data, which is collected for many single crystal orientations, so the intensity is measured as a function of scattering angle with two positions for the detectors. Then we have the energy, which is the third variable, and crystal orientation, the fourth variable. So through this fourth dimensional data set, we can extract slices of the intensity as a function of different directions in momentum and energy, and then extract dispersion points indicated by the dots from many directions in reciprocal space. Here's a picture of the relevant Boolean zone, and these are various directions along which we extract dispersion points. And then we can check with this dispersions data set whether it is fully consistent with the symmetry of the crystal structure and so on. And indeed, it's fully consistent with the Boolean zone with threefold symmetry as expected in this context. So if we start to parameterize this data, we consider first a single honeycomb layer with Heisenberg interactions, as I described in the introduction. So there's a magnetic Bragg peak here. There's the acoustic branch, which is quadratic for Heisenberg interaction, and this is one of the touching points. So this has some resemblance to the data in that there's a strong mode coming down here, and this is the touching point here. However, the data clearly shows near linear dispersions. So this could be explained by considering a strong easy plane part of the interaction. So if we consider an XY ferromagnet where spins interact only in the XY plane, then we get the linear dispersion. So of course, this is a 2D model, whereas we have a 3D crystal structure. So we need to add more exchanges. So the strategy that we adopt is to use an easy plane Hamiltonian, which has inequivalent parts for the spins in the plane and spin components out of the plane. And here, the spin is the spin of the magnetic ground state, because cobalt 2+ is a Kramer's ion with an odd number of electrons. Once it's placed in a crystal lattice, the combined effect of crystal field and spin-orbit coupling will lift the degeneracy down to a lowest Kramer's doublet, which can always be described by a pseudo-spin Baha. So within that formalism, we compare the data with a so-called XXZ Hamiltonian that would then have a different interaction J perpendicular for the components in the plane and J parallel for the components out of the plane. And then the exercise would be to add to J1, which is the nearest neighbor coupling, also other bonds, J2 for interlayer and various other interlayer couplings and second neighbor in planes and so on, until we get a good explanation of the measured dispersion relations. Now, one feature that's not explained by this model is the gap. that we clearly see above the Bragg peak. That's not explained because within this model, this has full continuous rotational symmetry around the z-axis. The spins would always be able to rotate in the plane, and that would be gapless. So we add the gap sort of by hand or empirically in quadrature to the dispersion relations that come from a Hamiltonian like this. And then including a number of further neighbor couplings up to the 6th nearest neighbor coupling, we can obtain a very good parameterization of all the modulations that we've seen in many places in the Brillouin zone. So this is a one-to-one correspondence between the observed energy and calculated energy over thousands of dispersion points with very good agreement. And you can also see here that the dispersions, the calculated dispersions go through the dispersion points. So not only the dispersions, but also the intensity distribution is well captured by this parameterization, in a sense that the strongest mode is indeed observed as predicted, and also the intensity sharing between the modes, which modes are strong, which are weak, and so on, is well captured. So one point I want to focus now is close to the nominal touching point. So these are close to, these are the corners of the Brillouin zone, and I'm going to show a slice going transversely like this. And we see here two modes that nearly linearly crossing at the K point. So one unusual feature here is that if we were to represent the conical dispersion surfaces touching at the K point and paint them with intensity as predicted by the theoretical model, this intensity is not uniform around the core, but it's strong on one side and very weak on the other side, and exactly in antiphase for the bottom band. So this the slice that I've showed here is in this transverse direction here, where both modes are clearly visible. However, if we were to scan along this direction, which corresponds to the radial direction out, then what we see experimentally is just a single mode, this one going out there. There is another mode out here, but this has zero intensity. Okay? There should be another mode here, but has zero intensity. And that's indeed as expected theoretically. There should be no intensity on this side, but all the intensity should be on this side. Now, another way to see this intensity asymmetry is to focus at a constant energy and look at the intensity distribution as a function of momentum. So in the top band, it's all on the right-hand side in this diagram, which corresponds to outside the first Brillouin zone here. So all the intensity is on the outside here. Whereas if we go to the bottom band, it should have moved to the inside. And indeed, all the intensity has now moved on the inside. Okay, it was outside and has moved on the inside. So let's look at this more closely. So if we expect to have an intensity distribution that winds as we move around the nodal point from strong to weak and so on, the best way to illustrate that is to look at the intensity as a function of a circular azimuthal angle moving around like this. So if we plot the intensity as a function of alpha, indeed we find a maximum, a minimum coming back, and then exactly an antiphase between the top and bottom band, as predicted theoretically through this distribution here. Now, this is a non-trivial effect. So if we add up the intensity in the two bands, we get something that's smooth, essentially constant. Okay? And to see that this is non-trivial, this intensity distribution is non-trivial, let's look at another conical dispersion surface, this time above the Bragg peak. Okay? So this is the Bragg peak. We know we have a small gap, and there's a conical dispersion above it. This is the experimental data. That's the Bragg peak. That's the dispersion relation. If we take a constant energy contour here, you see the intensity is uniform everywhere around here. So if we plot the intensity as a function of angle, we get a constant. So the fact that the intensity is very strongly modulated with angle, moving around the nodal point, is really a characteristic of linear band touching of these two bands. It's a fundamental property of the topological aspect of this linear touching point. And more quantitatively now, if we use the full J1, J6 model, actual positions of the cobalts and so on, this is the data, this is the calculation, looking at exactly the same azimuthal scans, same pixels, the data, the maximum in the calculation is in the same position as in the data and so on. So there's very good agreement capturing this intensity modulation. Now, one way to think about this intensity winding around the nodal points is in terms of the concept of isospin. So in the vicinity of linear band touching, the dispersion is linear like this. So it can be written in the form of a Zeeman term, where we have a radial magnetic field, V delta K. This is virtual, of course. And sigma stands for an isospin, which can have eigenvalues of ±1 along delta K. So this isospin is radially out for the top band, such that the energy is plus V delta K. And for the bottom band is radially in, such that the energy is minus V delta K. So that explains this linear dispersion. So this isospin is, of course, a property that is separate from the real spin of the magnon, because all magnons have delta Az minus 1. This isospin is really related to the wave function decomposition on the two A and B sublattices of the honeycomb. So one can see direct evidence of this isospin in the fact that the intensity in inelastic neutron scattering, which is the dynamical structure factor, is related to the projection of the isospin onto a characteristic vector n, which for the case of the first Brillouin zone is the vector that's radially out from the gamma point. So in this picture here, if we represent the characteristic vector n like this, now the isospin for the states in the top band is radially out at every point. And so we expect strong intensity, this red region here, where the isospin is parallel to the n vector. And then if we move around, when the isospin is anti-parallel with the n vector, we're expected to see cancellation under ideal conditions. And then the intensity to wind back up again. And to be exactly in opposite for the bottom band, to be 0 there and maximum on the other side. So that's the physical interpretation of the intensity modulations that we see in the data, is due to the isospin winding around the nodal point and being in opposite senses for the top and bottom band. And this type of intensity modulation is completely analogous to what's been seen by RPS measurements in doped graphene. So here is a constant energy RPS measurement at an energy just below the Fermi level. This is for doped graphene. And you see the intensity is non-uniform, but has a bright spot, dark spot, and comes back to bright. This is completely analogous to the intensity modulation here, strong, weak, strong. Because fundamentally, the form of the wave function and the same isospin concept also applies in this case. So this type of intensity modulation is a characteristic signature of the topological property of the nodal point. And in fact, there could be other more complex situations. For example, if one has quadratic band touching, where these bands are quadratic and not linear. And in that case, one expects a more complex periodic pattern as a function of angle with maxima, minima, maxima, minima. So multiple maximas and minimas. So now I want to show that rather similar features also happen in high energy excitations in this material, not just for magnons. Okay, so before that, let me explain in more detail the L dependence of this intensity modulation. So L is the vertical direction perpendicular to the layers. So if we pick one K point up here and do an azimuthal scan, then at L equals to 0, the maximum is a minus 60, which corresponds to this radial direction here. However, if we go at negative or positive L's, this maximum shifts, okay? Which suggests that the maximum will be here for negative L and here for positive L. So this intensity distribution is twofold at every L, but actually it spins round as one moves along the nodal line. This is represented here. Let me show an animation. Oh, no. So if we vary L, what's seen experimentally is that the region of strong intensity actually rotates round. So it's always in antiphase between top and bottom bands, but actually it rotates round as you move up along the L direction. So this puzzled us for a while, but actually it's very naturally explained if one considers the fact that the honeycomb is not planar, but is actually buckled. So the A and B sublattices are not at the same height, normal to the plane, but one is below and the other one is above the plane. And if one considers then hopping of magnons between the two sublattices, then in this hopping term, there's an additional phase factor associated with the projection of the wave vector onto the Z direction. And if we account for this additional phase, then this explains the rotation of the color pattern on these cones, both in magnitude and sense, compared to what's seen experimentally. Okay? And it also explains that adjacent points actually rotate in opposite directions. That's a requirement of inversion symmetry, which we also see experimentally. So we have a very good understanding of the intensity modulations in the two bands around the nodal points for magnons. And in the following, I'm going to show that very similar physics can be observed for higher energy excitations. So for that, let's consider the ground state of cobalt 2+ ion. So here we have 7 electrons. And for free ions, this would correspond to L equals to 3 and spin 3 halves. Now, in an octahedral cubic environment, the 7-fold orbital degeneracy is split into a lower triplet and some other states, triplet and singlet hierarchy. But this lower triplet is equivalent to an effective L equals to 1, and via spin-orbit coupling, then this gives rise to this energy diagram here, where the ground state is J effective 1/2. And via trigonal splitting, which occurs in the system because the octahedra are compressed along the z-axis, the stacking direction, this gives rise to a splitting here. And indeed, we do see experimentally transitions to these states that we identify with transitions in the trigonally split J3/2 level. So this is the blue transitions to the first level, and the red one is to the second level. So now measurements on single crystals show that actually this level disperses in reciprocal space in a very similar fashion that mimics the magnon dispersions at low energy. So this is the magnon dispersion, and here is the transition of the crystal field level or exciton at higher energies. And we can again analyze that and compare it with what we expect theoretically for excitons now hopping between the two sides of a honeycomb lattice. So the exciton is a local transition to an excited spin orbital state, and then through exchange, we expect that that can hop also onto sides of the lattice. And that's equivalent problem to, again, hopping on the honeycomb lattice as in graphene, but with an energy offset. So again, expect two bands that touch at the corners of the Brillouin zone. And the dispersion relations that we extract experimentally could be well parameterized theoretically, and also the intensities. And this explains why most of the places carry intensity just for one mode, but there's regions with intensity in both modes, as we see experimentally. So we can also look for evidence of narrowing of the spectrum close to the corners of the Brillouin zone. And indeed, the resolution here is not as good as the low energies, but still there's very clear narrowing and sharpening of the spectrum down to resolution limited at the K points here and there, and it's much broader in other places. And then we can do the same type of exercise by looking at the intensity distribution as a function of angle. And then we find an alternation between maximum, minimum, 180 degrees away, and in complete antiphase between the top and bottom bands of the excitons. And again, with an offset that's completely explained by the buckling of the honeycombs. So this isospin picture is actually quite universally describing both the intensity anomaly in the magnons and in the excitons. So now in the remaining time, I want to discuss the possible mechanism for the gap that we observe at low energies, which indicates a preferential in-plane orientation of the spins that's not captured by the parameterization and this XXZ main model that we've discussed so far. So what's surprising is that at the mean field level, no symmetry allowed bilinear exchange can lift this degeneracy, not even dipolar couplings. And let's consider, for example, a symmetry allow exchange that would prefer, say, for this bond, for the spins to be aligned along the bond direction. So that's an SX1, SX1 interaction. Now, by symmetry, there must be an interaction for this bond, that's SX2, SX2, and similar for the third bond. So if this is added up, it comes out to adding 3 cosines with a 2 pi by 3 offset. And even though cosine squares, and even though each one depends on theta, the sum of them is constant. And one can show more generally that for any type of bilinear couplings, there's no mechanism at the mean field level to select, to have the energy depend on theta. So we then are left with several other scenarios to consider. Potentially, the gap could be due to magnetoelastic effects because the magnetic order breaks the threefold rotational symmetry. However, there's no evidence in diffraction that the lattice has changed in any way. The lattice parameters A and B are identical to one another to better than 0.02%. So it's almost unchanged. So we then have to consider within the constraints of threefold symmetry, what other possibilities exist. And one natural scenario is order by disorder by quantum fluctuations, where there's an additional contribution to the ground state energy due to 0-point fluctuations. And this does depend on theta, so this could select. And another possibility is that we consider the unquenched orbital moment, and through orbital fluctuations, they may select the ground state. So I'm going to consider each of these scenarios in turn. So let's consider that we have on the nearest neighbor bonds, we have different exchange interactions for the spin components that are along the bonds and perpendicular. This is certainly allowed by symmetry. So in other words, we have an eta term here that is non-zero. Now, at the mean field level, the ground state doesn't depend on the orientation of the spin's psi with respect to some reference direction, but the spin wave spectrum would depend on psi. And so in the harmonic spin wave approximation, where the energy is n plus a half h bar omega, this a half h bar omega constitutes the 0-point energy. And if we sum this up for all points in the Brillouin zone of all bands, we indeed find this quantum contribution of the energy to depend on angle psi. and in fact have the expected six-fold degeneracy, six-fold periodicity. So it's threefold because of the threefold of the lattice and the fact that spins rotating 180 degrees don't change the energy. So indeed, this could provide a mechanism to select orientation, say for spins to be along or perpendicular to the bonds. And then doing various scaling analysis, we find that the gap indeed varies with this anisotropy to some power. And of course, we know that the XXZ Hamiltonian provides a reasonable description of the data almost everywhere except the gap. So we're looking for a gap scenario that would not change things only very little in other parts of the zone. And this eta interaction actually does do that because adding it up only makes very small changes between the red and blue lines here. And most changes are on the brilliant zone boundary. And one particular feature here is that in the presence of this anisotropic interaction, the touching points are still intact, but they're no longer symmetry restricted to be at the K point, but they can shift. So in the pure XXZ model, the touching point is exactly at the K point, but in the presence of finite eta anisotropy, this is expected to shift. In other words, the spectrum no longer has threefold symmetry, but only inversion symmetry, and there is a compression of the dispersions along a direction related to the ordered moment. So we expect that the spectrum will shift away from the K point. So then, by doing a scan exactly at the K point, one would expect to see a splitting, so two peaks rather than a single peak. And indeed, this is seen experimentally if we look very carefully. So if we do a slice here precisely at the K point, the expectation of the XXZ model is that really they should touch in a very sharp point here. But if we look carefully at the data, there's some broadening here that's beyond the broadening of a single dispersion. And in fact, if we do a scan up here, there's clearly two peaks, whereas if it was the XXZ model, we'd expect a single peak. And the blue line is actually a fit where we vary this anisotropy interaction eta. So the amount of splitting gives us a measure of how strong this anisotropic interaction can be. And some finite interaction actually is compatible with the experimental results. Now, does that explain the actual physics in this material? So we've shown that this anisotropic interaction can provide a minimal model within the effective spin-and-a-half picture to explain fundamentally why there should be a ground state selection, why there should be a gap, and then also other features in the experimental data, this fine structure for K-point scans and some additional splitting on the zone boundaries, they can all be explained qualitatively. However, one difficulty with this explanation is that in order to observe the gap that we see experimentally at 1 MeV, we need quite a large anisotropy that then is not compatible with the high energy changes. So then we're looking for another possible mechanism. And so for that, I want to come back to consider the other degrees of freedom in the system, the orbital degrees of freedom. So just to remind you, so far, all the analysis that we have performed is considering only fluctuations within this lowest Kramer's doublet. However, because here the crystal field splitting, the spin-orbit interaction, and the magnetic exchange are all comparable, one should really treat the full spin and orbital space together and not completely assume that the orbital degrees of freedom are completely quenched. And so using that approach, so if we work, if we then work into the lowest orbital triplet manifold, where we have an orbital degree of freedom L equals to 1, and in the have a spin, quantum number spin 3.5, that gives rise to 12 states. So if we work in the basis of full 12 spin orbital states for L equals to 1 and spin 3.5, then we add the spin orbit coupling, lambda ls. We can add the trigonal splitting, which depends on the LZ component. And then we can add some exchange interaction. So the first two terms are single ion terms, and they give rise to the splitting of the crystal field levels. Now, if we project this Heisenberg exchange onto the level splitting induced by the first two terms, we get the XXZ Hamiltonian. Because this trigonal splitting prefers the spins to be in the plane. So we need to go beyond this in order to add additional interactions that could potentially explain the gap. So now for cobalt 2+, the electrons, the unpaired electrons are in d orbitals, and they can be of the form T2g or EG, where T2g orbitals are sort of threefold orbitals like this that are confined to the XY, YZ, or ZX plane. So if we consider here an idealized geometry of cobalt, oxygen, cobalt exchange, then we have to take into account the specific orbitals through which exchange can happen. So for example, this blue colored orbital here labeled A can have an exchange via the oxygen with the blue, sorry, with the green orbital labeled B here. So we can have an exchange between the A orbital and the B orbital here. So this bond directional exchange introduces additional anisotropy. So there are exchange terms that contain a spin part and an orbital part, as I've indicated here, through the A and B orbitals. And similarly, one can have other types of spin and orbital exchange. And because the magnetic moment in the ground state contains both a spin and an orbital part, then there will be an energy contribution that will depend on the magnetic moment orientation in the ground state. And we indeed find that if a model that contains these three key terms and one spin orbital exchange, if the magnetic ground state is considered at the mean field level, then there is an energy contribution that depends on the angle psi of the magnetic moment in the ground state. And so this provides a mechanism for ground state selection. And as a consequence, by calculating excitations of this in a generalized spin wave formalism, so-called flavor wave, then one finds a gap. I'm illustrating here the results of the magnon dispersions if we put some representative values for these exchange interactions. So here, because this is a much complex calculation, it's not possible to do the same type of comprehensive fitting and variation in phase space as we've done before. But by trialing a number of combinations of exchanges, we can find sets that produce dispersion relations that are similar bandwidth to the magnon dispersions. For example, here, this is the experimental data, and this is the calculation for the magnons. So we have the linearly dispersive strong mode here, and all the key features are really reproduced. Okay? There's a gap mode here that's weaker in intensity from that one. There's two modes here. Here, both carry intensity. Here, only one intensity. We think these are fine details that potentially could be remedied by doing a full fit of this. Now, the important part is that if we add a spin orbital exchange, then the dispersions are essentially unchanged at high energies compared to before, but a gap appears, okay, and as seen experimentally. And then this flavor wave picture provides a mechanism not only to explain the magnons, but also to explain the high energy excitons. And here is the calculation, and resembles very closely the data. And this is a non-trivial agreement because we've used essentially the same exchange interactions via projection to describe both the exciton dispersion and the magnon dispersion. So fundamentally, it's the same exchange that produces hopping, but for different types of quasiparticles. So this flavor wave picture with spin-orbital exchange can provide a mechanism to capture within a single framework both the gap magnons and also the spin-orbit excitons. So just to summarize our main results, so we've explored the manifestation of linear band touchings in Honeycomb cobalt titanate, which exemplifies Dirac nodal lines for both magnons and spin-orbit excitons. We have seen a two-fold periodic intensity modulation in azimuthal scans around the Dirac nodes, as expected from this isospin winding picture. And one aspect that was quite surprising to resolve in the experiment was the presence of a gap above the magnetic back peaks, which indicate a preference for certain discrete directions in the plane. And this cannot be understood semi-classically. And we've discussed two possible scenarios to explain this. One involves quantum fluctuations. So there is a contribution to the ground state energy from zero-point quantum fluctuations, and some directions could have higher zero-point energy gain than others, and that could provide a mechanism for this. And another possibility is that because in this system, the magnetic exchange, spin-orbit coupling, and crystal field splitting are all of comparable magnitude, one has to treat on equal footing both the spin and the orbital degrees of freedom. So here, we've also found a mechanism for ground state selection in that the magnetic moments have both a spin and an orbital part, and then fluctuations of the orbital bit through virtual crystal field excitations can add an energy term that would select preferential directions in the plane as opposed to others. So the phenomenon of selecting a unique ground state from a classical manifold of degenerate ground states, it's quite a fundamental interest in frustrated magnetism, and cases of order by disorder that are really clear, so found experimentally, are very rare. This is quite a unique circumstance in which the exchange, spin-orbit coupling, and crystal field interactions are all comparable. So most likely, the ground state selection is through virtual crystal field transitions. In other systems, such as erbium titanate, which is quite a canonical example of order by disorder, the separation of energy scales is much larger. So probably there, that mechanism is not so relevant. But here, it could be, it looks like, in our opinion, is the most relevant. Of course, in terms of exploring topological signatures, we've looked at simplest lattice, honeycomb lattice. However, this kind of band touchings can occur on more general lattices and could be even more complex, not just linear band touching, but quadratic. And even in that case, there are very specific signatures for the intensity modulations. So potentially, the techniques that we've developed here could be more generally applied to study these kinds of band touchings also in much more complex systems. I thank you very much for your attention.
All right, thanks Radu for a great talk. Yeah, sorry, it's hard to have applause on Zoom. So I'll open up the floor. I think we have time for a few questions. If anybody has them, you can put them in the chat or just ask out.
I have a question.
Go ahead, Sean.
Please, yes.
Okay, so for that buckling, if you find that, go back to that picture.
Sorry, which?
The honeycomb lattice breaks into two triangular lattice.
Honeycomb lattice. Is that early on or?
Where you showed the buckling of the honeycomb lattice?
Oh, the buckling. Oh, yes, 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 yes.
Yes. So is that a piracy effect?
No, no, no. This is just a property of the crystal lattice. So
why does it buckle? Why does it buckle?
It's because of the bonding geometry. I'll just go back to the crystal structure.
So it was preferred by the interatomic bonding?
So so there's another layer here of titanium atoms that also forms a honeycomb edge-shared octahedral lattice. And it's just the way these are bonded that one octahedron is slightly above the plane and the other one is slightly below the plane. And that's in tandem with what happens to the titanium.
So strictly speaking, this is not really honeycomb lattice, right? It's just two triangular lattice sitting on top of each other. Sort of looks close to a honeycomb lattice, but not really.
So in projection, it's a honeycomb network. Mm-hmm. I would say it's a buckled honeycomb structure. There's still inversion symmetry at the midpoint between the A and B sides. Just that the A sides are all a bit above the plane and B sides are all below. Mm-hmm. I mean, this is really it doesn't change the periodicity of the lattice, or some symmetry elements are gone, some mirror planes are gone and so on. But the threefold and the inversion symmetry are still present. But for example, there's no longer a mirror plane vertically here. That's because this oxygen can't map into that. I mean, the oxygens already break the some mirror planes that happen for the ideal honeycomb plane, but don't happen here. But this type of buckling shouldn't change the nature of the symmetries that guarantee the nodal points.
Mm-hmm. Thank you.
I guess so. I'll ask a question. So you showed a nice quantitative analysis to make a convincing case that these sorts of topologically protected band structures show up in magnetic excitations and orbital excitations. I'm wondering if you have any kind of general comment about what might be some kinds of advantages of studying these sorts of topological states in magnetic systems as opposed to purely electronic ones like graphene.
Yeah, so this is a great question. So of course, one can't do the same type of experiments as in the electronic systems because these are all excited states. So, but one advantage in the context of magnetic systems is that these excitations carry spin. So in principle, with magnetic field, one can manipulate the dispersion relations. And there are theoretical scenarios predicted, in fact, where in three-dimensional systems, there are two wild nodes that are pairs of each other. And with magnetic field, by changing the field direction, they can spin in a reciprocal space, depending on how the magnetic field is rotated, or they can even move towards one another and annihilate themselves. So there's a range of potential experiments that could be done on magnetic systems to manipulate these nodal points and see that experimentally. That's not so easy in electronic systems, but it's different kinds of experiments.
Right. So would one have to look at spin transport types of quantities, or just mapping the band structures with neutron scattering?
So in terms of seeing the phenomenology of paired wild nodes annihilating one another and so on, that would all be similar techniques to what I've shown here. Potentially there could be magnetic effects on the surface, but I really have no deep understanding as to how to experimentally probe those. But potentially there could be effects associated with that.
And then just to kind of follow up related, I guess, so the purely magnetic excitations could be manipulated with field. Do you think there's maybe possibilities for things like strain to manipulate the orbital topologically?
Yeah, so strain is really potentially a very useful technique, whether experimentally there are challenges. But
yes,
via strain or pressure, uniaxial pressure, one could potentially explore this phase diagram. So go from octahedra that are squashed to close to cubic and close to elongated, and completely tune the crystal field environment, and potentially even get closer to this regime of more isotropic couplings. I mean, more sort of maybe a less ambitious aim in the context of this project would be to try and select one of the 6 magnetic domains via strain. That already would be quite something, because it would enable a much more detailed test of the specific anisotropic interactions that are present. Because we know that in our sample we have these 6 domains. Of course, 3 are related by 120 degrees, and then each one can have spin reversed. Now the reversed ones, pairs, have identical dispersions, but the other ones have slightly different dispersions. So there could be potentially some detailed information about what happens close to the touching points, which direction they move, and so on. That if we're able to use strain on a neutron size inelastic neutron size sample in a controlled way, and select a single domain, that could potentially give some additional information about the mechanism of the ground state selection and so on. That could distinguish between scenarios. But there are technical challenges in implementing strain on large crystals, and
you probably want to, if you could do it with X-rays, that might help, but I don't know what you could measure exactly.
Would have to think more about that.
I have another question, but I'll wait and see for a minute. We're also a little bit above time, so I guess I'll ask quickly. So does the final analysis, your sort of flavor wave analysis where you had to include orbital parameters, I wonder if it gives any kind of more broader clues about how one might move into this spin liquid regime from the regime where you think cobalt titanate is currently in, or how you might maybe better design some other compounds to move into this sort of spin liquid regime, or maybe it does not have that sort of far reaching.
So I mean, the key ingredient of the Kitaev spin liquid is that you have an equal balance between the interactions along 3 bonds. So you're in the cubic limit. So that really is exemplified here, that the blue region is really centered around 0 trigonal distortion.
Right,
So,
but actually, I thought when you had differences on the 3 bonds, you could go from a gapless to the topological spin liquid, right? If you have, say,
yes, but that's not. So the trigonal distortion is not introducing competition between between the Ising bond along this direction and the Ising bond along that and the Ising bond along this. But it's actually introducing Heisenberg terms and gamma terms and so on that are competing with the Kitaev terms. But all this trigonal distortion actually maintains the symmetry between these 3 bonds. But the interaction is no longer Ising-like, but it's mixed in with, so in this case up here is strongly in the plane, and in this red region here is strongly along a common c-axis. So for the Kitaev spin liquid, you need the Ising axis to rotate with the bond. So to be very close to the cubic symmetry. And in fact, this work up here gives as much insight as can be obtained at this point from this phase diagram. And they use exactly, I mean, we've used exactly the same spin orbital exchanges as they propose.
okay.
And there's a mechanism from these spin orbital exchanges to project in this blue region to something that's predominantly the Kitaev Hamiltonian. That's why this phase is stable in that region.
I see.
So really the key parameter to change is the trigonal distortion. If we get closer to the cubic limit, that's, according to all the theoretical models proposed so far, that would be the place where the strongest competing interactions would occur.
Okay.
So we know that in cobalt titanate, there are bond-dependent interactions, but they're not dominant. But we see evidence that they're there, but they're not dominant. We need to go to the regime where they become dominant.
Yeah. And then, so I mean, as compared to the 5D or 4D compounds, another competing interaction is just direct exchange, right? I guess that's weaker in cobalt because the 3D orbitals are smaller.
That's right. That's what Ginyard Kaliulin proposes in this paper here, that the direct exchange is weaker. And in fact, the exchange from the thing that's different here is that you have EG electrons. And the EG electrons tend to have a Heisenberg interaction that's antiferromagnetic, and T2G that's ferromagnetic. So they tend to cancel each other and help the Kitaev. So this EG part is missing from the 4D and 5D. So potentially in 3D, having slightly different spin orbital ground state could potentially help get closer to this limit.
I see.
And another material that's in this phase diagram is this sodium cobalt antimony oxide, and that's here. Now it turns out that the crystal field splitting is almost similar between the two, so they're probably similar somewhere on this line, both of them. We don't know where this one is, whether it's close to this boundary or further away, but both of them may be similarly away from this phase.
So maybe you don't want to make such a bold statement, but do you think perhaps cobalt is a more promising system for looking for Kitaev physics compared to iridium or ruthenium, or it's just a different system and we should just look everywhere?
Yeah, I think it's a different system. We should just look.
Yeah. Okay.
Yeah. And potentially, they, having a wider range of materials with slightly different electronic grounds and so on, it gives a better chance of seeing physics close to the Kitaev at some point. And maybe some are more tunable than others.
Yes.
Certainly, it's possible to obtain experimentally much larger crystals of the cobalt oxides than all of the rutheniates and iridates so far.
Yes.
And also, there's no problems with absorption. So no, there's experimental opportunities there.
Yeah.
And maybe the energy scale can be manipulated with field and so on. So it's another class that adds to the fold.
Great. Okay, so I think we've gone 20 minutes past. I think I'll keep hanging around if there was a graduate student or somebody who wanted to ask a question but they're too nervous. Now's the time to do so. If not, I guess I'll just thank you again, Radu, for a great talk.
Yeah, thank you for the opportunity.
Very interesting.
Yeah, your questions. Thank you. Okay, thank you very much.
Okay, yeah, thanks.
Everyone,
yeah. See you.
Yeah, take care. Okay, thank you. Bye.
Yes, hopefully I'll, yeah.